will start. Okay, so today I'm going to talk about luminous blue variables. This work is done mainly with my PhD advisor, Dr. Jeremiah Murphy, and Dr. Nathan Smith, who I'm currently working with as a postdoc at the University of Arizona. So our main goal is to use parallaxes and proper motions from Gaia Space Mission to constrain the evolution of massive stars. The two main features that determine massive stars' evolution is their mass and mass loss. Gaia parallaxes will help us to constrain massive stars' mass and luminosities, and using Gaia kinematics, we can constrain their ages. And using these mass and age estimates, we can constrain different mass loss phases. One important yet uncertain mass loss phase represented by luminous blue variables, or LBVs, which is the focus of my today's talk. But what are luminous blue variables, or LBVs? LBV is an observational phenomenon, is not a theoretical idea, and they are very luminous stars. Their luminosities corresponds to initial masses around 50 solar mass, and they are sometimes blue and they're sometimes variables. Usually LBVs experience either S-star variability or giant eruptions. S-star variables, they usually lie in this blue diagonal shaped region known as S-star instability strip in the HR diagram, which is their hot blue state. And during their outbursts, they move to the red side of the HR diagram, which is the red cool state. In the transition between these two stages, they usually, but not always, have constant volumetric luminosities. And S-star variables, they are not major mass loss events, but some LBVs like P Cygni or Aghakhanloo, they experience giant eruptions. For example, here you can see light curve of Aghakhanloo during its outburst. Giant eruptions are major eruptive mass loss events, and they usually show a strong increase in their volumetric luminosities. So before going through the details of my work, I would like to give you the takeaway points of my research. So we modeled the LBV's isolation, and we found that LBVs should be product of binary evolution. Then we used Gaia parallaxes, and we inferred how far away most of the galactic LBVs are. We found that nearly half of them, they're closer than what previously estimated, which makes them less luminous, less massive stars, which is more consistent with the binary evolution rather than single star scenario. And for one of the galactic LBVs, LBV W243, we used its associated cluster, and we inferred more accurate distance estimate to this LBV. So now let's dive into the details. In a single star scenario, LBVs are brief transitional phase when their hydrogen envelope is removed by winds or eruptions, propelling the star to become a Wolf star. In this scenario, LBVs should be close to other massive stars like early O stars. However, Smith and Thomas in 2015 found that LBVs are isolated from O stars. For example, here you can see one of their plots, which is the separation to the nearest O star for different type of stars. For example, in green, we have early O stars, then we have mid, in blue, we have late type O stars, and in purple, we have Wolf stars, and black is the LBV separation distribution. They found that LBVs are a factor of 10 more separated than early O stars. And interestingly, they are even more isolated than Wolf stars, which is totally inconsistent with the single star scenario. So they propose that LBVs are isolated either because they are mergers or they are kicked mass gainers and they receive a kick from their companion supernova explosion. So in my first work, we developed an analytical model to test this idea. To model isolation of LBVs, first we have to model the passive dissolution of young clusters. And for that, we propose a Monte Carlo model for separation between O stars by considering random sample of clusters at random ages. For example, here you can see 3 randomly generated clusters at their random ages. And the separation between the stars increases because the clusters is dispersing with dispersal velocity v sub d, and all stars are disappearing as they evolve. So now we can compare passive dissolution model with the data to infer drift velocity of O stars and then expand it to LBVs. Here we have mean separation to the nearest O star as a function of drift velocity. The dashed line represent our passive dissolution model for different type of O stars, and the solid lines are the observed average separation of O stars from nearest O star. By comparing the data with a model, we found that lower mass stars, they have higher drift velocities. And then we expand this model to model the isolation of LBVs. Here we have separation as a function of age. The orange curve is our passive dissolution model, and the brown solid line is the observed average separation of LBVs to the nearest O star. If LBVs are single stars, then they reach to the observed separations around 9 million years, which corresponds to an initial mass of around 2021 solar mass. However, as I said at the beginning of my talk, LBVs are very luminous stars, and their luminosities corresponds to initial masses around 50. So clearly, as single stars, they don't have enough time to reach the observed separations, unless either they are somehow overluminous or they are rejuvenated stars. So either they can be mergers or they can be kicked mass gainers. So here you can see drift velocity of LBVs as a function of age. The blue curves are again our passive dissolution model, and the black solid lines the drift velocity of mid-type O stars just as a reference. On the right side is where LBVs are older than what they look like, and they don't need any extra velocity to reach the observed separations. In this case, they are mergers. On the left side is where they are massive and young stars, let's say around 3 million years. In this case, they need velocities around 100, 110, in addition to the drift velocity of mid-type O stars to reach the observed separations. And in between is a combination of both. So if they gain more mass from their companion, they need less kick velocity to reach the observed separations, and vice versa. So here we are showing that if LBVs are kick mass gainers, their kick velocities can be anywhere between 0 to 100, 110 kilometers per second. They don't need to always have really high velocities to be considered as kicked. So LBV's isolation suggests that LBVs should be product of binary evolution. However, specifically for galactic LBVs, it's hard to constrain whether they are mergers or they're kick mass gainers or maybe both because of their uncertain mass and age, because of their uncertain mass and ages. And that is because of their uncertain distances. So using Gaia DR2, we inferred how far away galactic LBVs are. Here you can see our Bayesian inference distances versus the previous distance estimate in the literature. We found that nearly half of them, they're closer than what previously estimated in the literature. So if we put them back in the HR diagram, you can see the red circles are LBVs based on their previous distance estimates in the literature, and the black circles are LBVs based on their new Gaia DR2 distances. So you can see that nearly half of them, they're at lower luminosities. This means that either these stars are mistakenly classified as LBVs, which is unlikely because most of them, they're confirmed LBVs. The field circles are confirmed LBVs. Or the S-star instability should be wider. So we decided to use the associated clusters to reduce these error bars. However, as I mentioned many times, LBVs are isolated, so it's not straightforward to figure out where they're coming from to use the associated clusters. However, for one of these LBVs, LBV W243 is known to be associated to a cluster known as Westerland 1, which we heard about it in the first day. Westerland 1 is a really famous cluster. It has one confirmed LBV, it has one magnetar, wolf stars, red supergiants, yellow hypergiants. So if we infer how far away this cluster is, we can constrain fundamental parameters of all the cluster members, including the LBV and the magnetar. In the left side, you can see position of stars within 10 arcminutes of Westerland 1. The inner circle marks 1 arcminute and the outer ring is from 9 to 10 arcminutes. The density of the stars noticeably increases towards the center. And on the right side, you see average parallax as a function of radius. The average parallax increases till around 2.5 arcminutes, and then is constant. So most of the stars in the inner circle are associated with the cluster members, and most of the stars in the outer ring are associated with the field stars. So using these stars, we modeled both cluster and field stars. And using the Bayesian inference, we inferred how far away Westerland 1 is. We inferred that Westerland 1 is around 2.6 kiloparsec away. And then using the Gaia DR3, we found a similar value of around 2.8 kiloparsec. So if we put,
2 minutes left, Mojgan.
Great. So if we use the new Gaia DR2 distance estimate to Westerlund 1, here you can see the cluster members in the HR diagram. The field circles are based on their new Gaia DR2 distance estimates, and the empty ones are based on the most common previous distance estimate to Westerlund 1, which is around 5 kiloparsec. Clearly, the LBV W243 was part of the in transition between these two stages using the previous distance estimate, but now is a lot less massive, less luminous, and is around the edge of the external stability strip. You can see Wolf-Rayet stars in purple, yellow hypergiants, red supergiants. So Westerlund 1, based on the new Gaia DR2 distance estimate, is a lot less massive and a lot more older cluster. And the initial mass of LBV W243 and a magnetar reduced from 40 solar mass to 22, which is more consistent with the single star, with the binary evolution rather than single star scenario. So in my first work, we model LBV's isolation, and we found that LBVs are isolated because they should be product of binary evolution. And then we used Gaia parallaxes, and we inferred how far away galactic LBVs are. And we found that they are nearly half of them, they are closer, which makes them less luminous, less massive stars, again, more consistent with the binary evolution. And we found that LBV W243 and the magnetar associated with Westerlund 1, they have initial masses a little bit above 20 solar masses, which is again consistent with the binary evolution. And with that, I will conclude.